Okay. Okay, I hope my screen is visible. Okay, so let me go to presentation mode, but just before going there, let me ask you a question. Have you tried different GDB features? We have told you quite a lot of things. Okay, but have you tried those things yourselves?
Yes, sir.
Okay, things are working,
Yes,
right?
sir.
Yes, sir. Also for the function
Yes, sir.
calls, it's working in my machine. It's not showing arbitrary values.
Means?
Sir, in some places in the slides.
Oh, okay. I understand. Okay, yeah, it's good. For my machine, it's happening. Why I didn't figure out. Yeah. But anyway, if it comes fine with your machine, no problem actually. Yeah. So let us do something little different today. So this is yet another kind of debugging tool called Valgrind. It can do a lot of things actually, but for you, telling all these things is a bit too complicated at this stage. Okay. So we'll actually use what is called the memory check module of Valgrind. Okay. So this will allow you to solve a lot of problems with memory. Okay, some memory related issues. We will see one by one. Okay, first of all, this name looks like a complicated thing, Valgrind, and it may appear that this is an abbreviation of value grinder, but actually it is not so. It is not a value grinder. It is actually derived from some Norse mythology. Okay, so there is a big hall, a huge hall of the dead or killed people called Valhalla, and it has a gate, okay, opening entrance that is called Valgrind. For some reason, the designers thought about using this name, so we'll stick to this anyway. What's there in a name anyway? Yeah. So in our case, we will use this Valgrind not as an entrance to the hall of this lane, but as a memory debugging tool. Okay, so what it is? Yeah, so it is capable of detecting several common memory related problems and errors also. Okay, so and also sometimes some kind of memory related profiling it does. So we will see one by one. So we will, as I mentioned, we will only use the mem check feature, okay, memory check feature of Valgrind. It can do a lot of other things, but these things are well beyond the scope of your understanding at this stage. Maybe in future, when you learn what cache memory is, you can also use the cache check feature and all that stuff. But anyway, for the moment, let us restrict our attention only to the memory check features. And there are two common problems with programs using memory, particularly dynamically allocated memory. One is called memory leak. And second, which not only I would say is restricted to dynamic memories, is also true for static memory, static arrays. So this is invalid memory access. Okay. So why these two things are important? Let us understand this thing little bit. Okay. So memory leak has to do with only some dynamic memory. So you allocate memory uh, often for many purposes. Okay, using malloc, calloc, or even new if you use C++. Okay, then it is a good practice that whatever memory you allocate, before your program terminates, you simply free that memory. Okay, all the memory that you have allocated. Okay, why is that necessary? The necessity comes from the fact that so you have allocated some memory, so it's given to you. And unless you explicitly free that memory, nobody else can access it. Okay. Now, when your program terminates, it depends on the system. Your unused memory or unfreed memory should go back to the system pool. But whether the system will do that or not, you do not know. Moreover, you often write something like server kind of a daemon kind of programs, which always keeps running. They do not end actually. It keeps on waiting and some request comes, it handles the request, and then once again keeps on sleeping. Okay. So if you have a daemon-like program, and if it during, let's say, request services does some kind of memory allocation, but does not, free that memory, okay, even when it is no longer needed, then this unused, unfreed memory eventually may eat up your entire, I would say, available RAM. It may even go to the so-called swap area and all that stuff, and eventually you run out of memory. Okay, that's not a good practice. So the point is that if you allocate a memory, it's always a good, I would say, programming discipline to free that memory when this is no longer in use. Okay, so that is what is called memory leak.
Eddie, can I interrupt for a second?
Yeah.
Okay. Actually, it's extremely important. Okay, not you should, but you must make a practice. For the second kind of programs, the server programs that Eddie talked about. So in industry like you will not, your code will not pass if you have, so think of a web server. Okay, the server is running, every time you make a request to it, a thread gets created for you, it serves your request. Okay, but there is this one common memory pool from which each of those threads gets their memory. So for each of these threads, for serving your request, even if it leaks like a few bytes of memory, okay, just imagine a server that has to run continuously for 6 months without being shut or something and handles like millions of requests per day. Okay, this 2 bytes will just load up and the server will eventually crash. So when you actually check in your code and all, memory leak is a big test basically, that you're not allowed to, for long running servers, you're not allowed to leak even like 2-3 bytes of memory per request basically. That's how critical it is. If you terminate, the memory comes back to you, the system. But many of these, as Arias pointed out, many of these server demands will just keep on running. You're not allowed to shut down a server for like sometimes couple of hours over months basically. So just, in your head kind of practice that even though you are going to write very small programs and all, always think whatever I allocate has to be freed, even if it is 1 byte. So kind of get into that mindset. Thanks, Eddie.
Yeah. So this is first thing. Second thing is that C does never impose any kind of, I would say, out of the access area access to your, what is that called, arrays. Okay, for example, if you allocate an int array of size 100, you can access the 101st element, 200th element, even minus 100th element. Okay. So in C, there is no range checking. Okay. And therefore, C allows it to do this. And if you do so, two things may happen. First of all, you are corrupting memory. okay, which legally does not belong to your arrays. There may be something else sitting there. You are simply overwriting those things. That's a bad thing. Your other variables may get corrupt. Another possibility is that eventually you access something which is not even in your permission. So in that case, segmentation fault will occur. Okay. Therefore, but unfortunately, C does not impose any restriction on beyond the limit accesses. Okay. But using Valgrind, you can check some such, I would say, illegal memory accesses. Okay. So this is another very useful thing. The first one is, I would say, a must practice for every large programmer. And the second one is even for small programs, this may be a very critical issue. Okay, you may see your memory getting corrupted, other variables getting corrupted. You may encounter segmentation fault. Okay, and C does not have any automatic mechanism to even detect there is some such runtime error. Valgrind actually does it for you. Okay. So first of all, how you use Valgrind? Okay. Otherwise, whatever it does, you cannot do the thing. So suppose you want to run a.out with some options. Okay, option 1, option 2, option 3. So instead of running it directly, you just type Valgrind, that thing. Okay. Valgrind a.out, option 1, option 2, option 3, if there are any options at all. Okay. And this is very similar to GDB a.out. So instead of GDB a.out, you now write Valgrind a.out. Okay. And here are three just parameters, 2022 minus name, this, whatever, anyway. So this is a sample Valgrind output. Okay. So you are actually invoking the memcheck module of Valgrind. So it says memcheck, and you will see a lot of things like this. So this 4825 is basically the process ID. Okay. Maybe we will talk a little bit about this PID and all the stuff later. Okay. And then some small message and input output of your program, whatever your program, I would say, is supposed to read from the keyboard, whatever it outputs. Okay, all these things will appear here. So normal run of the program. In the end, okay, it will give a summary. Okay. So this is actually your goal. Okay. Whenever your program has no memory leak, it will say in use at exit 0 bytes in 0 blocks. Okay. But it will also say that total heap usage, you have made 23 allocs, you have made 23 frees. This much memory was allocated, but eventually everything is freed. All heap blocks are freed, no byte in use during exit, and therefore no leaks are possible. Okay. So this is the goal. So I will soon tell you what happens if you do not reach this goal, that you have made some allocs, do not free, then something will appear here instead of 0 bytes, and all heap blocks are free. This will also not be there. Okay, but remember that this is the ultimate goal. The heap summary should be like this: 0 errors from 0 context. Okay. And another thing, this happens only when your program terminates. Just before termination, Valgrind checks what mischiefs you have done, your program has done, and it will give you a summary of all these mischiefs. Okay. But during the execution of the program, if you ever want to access memory which is not allocated to your array, okay, and during this program, during the run of this program itself, it will issue some error or warning messages to the effect that you are now accessing some array elements which are not legally part of the array. Okay. So these two features we will see. First of all, let us see this part. Okay, how you should behave nicely with respect to your heap. Okay, in fact, if you remember or if you know it at all dynamic memory is allocated from the so-called heap. Okay, there is a heap part in your memory, there is a stack part in your memory. So heap is essentially associated with your dynamic memory. So this is listed here. Okay, and note that this is our goal. All heap blocks are freed, no leaks are possible. This is what we want to achieve. Okay. Okay, so what is a memory leak? I have already mentioned. Memory is allocated in blocks by malloc, calloc, realloc. So these are standard alloc commands, memory allocation command. And you can add in C++ new, that kind of thing, which also behaves like the same. And allocated memory should be freed, or in terms of AG, must be freed when no longer in use. So there are actually three types of memory, which is allocated but not freed. Okay, and Valgrind will detect each of these three or four types of, I would say, unfreed memory. One is called reachable. Okay, blocks that are not freed but still can be accessed until the end of the program using some pointers. Okay, so these are called reachable blocks. Okay, we will see an example. Then another type of memory definitely lost, which means blocks which are not only not freed but also not accessible by any pointer. Okay, so you didn't free it, got rid of this memory from your program, and you didn't bother to free that memory, and you didn't even bother to keep a pointer to that memory. Okay, so that is called definitely lost. Then there is something called indefinitely lost or indirectly lost. So again, blocks that are not freed, but they have some pointers pointing to them. But these pointers are present in other blocks, other lost blocks, or other definitely or indirectly lost blocks. Okay. So they have some pointers pointing to them, but those pointers reside in blocks which are definitely lost or already indirectly lost. Okay. And there is a third type, there is a fourth type of memory, possibly lost. So it's something like this. Okay, of course, if you do not see examples, you cannot understand these things fully now. Blocks are not freed and accessible only by pointers in their interiors. Okay. I will tell you that later. Okay. So you recall that if you malloc or use calloc or realloc, so this returns a pointer. Only that pointer can be freed. Okay, that +1 cannot be freed. That -1 cannot be freed. Okay. So these internal pointers are some pointers that do not point to the beginning of that memory location that was allocated, but somewhere in between. Okay. So this is called possibly lost because Valgrind exactly doesn't know whether from this internal pointer you can come back to the beginning of that block and free it. Okay, so we will see examples. And definitely invalid memory access, read or write a memory location outside the allocated area of an array. And it doesn't matter whether it's dynamically allocated or statically allocated. But I think Valgrind specializes in static arrays, as far as I remember. Okay, so I will give you examples of all these different types of things and also this. Okay, invalid memory access. So what I will do, I will implement something like a sorted linked list of integer data singly linked list. So there is a next pointer and this integer data. And in my machine, size of node is 16. It may be 8 in other machines, even more than 16 in some other machine, but 16 is possibly a very standard size of in current, I would say, architectures, standard Intel architectures with Ubuntu. This is possibly a good thing because this int is essentially 4 bytes. And in my machine, these are 8-byte addresses. So total 12 bytes, but usually blocks are allocated in I would say, or these structures are allocated in multiples of 8. So it's 16. Anyway, whatever it is, this number 16 you keep in your mind. Okay. We will see why 16 is important. Okay. So in my implementation, what I will do, I will always maintain a dummy node at the beginning of the list. So it does not contain any useful data item. Instead, this actually helps me in insert and delete. Okay. So for insert and delete, I should be in the node before the insertion or deletion position, right? But if you do insertion or deletion at the head, at the beginning, there is no node before it. That creates a trouble. And therefore, it's sometimes people prefer to use a dummy node at the beginning. Anyway, so you can. I am mentioning this because this dummy node is what you should understand because you have to count that node. Otherwise, whether your implementation contains a dummy node or not, it's up to you. I am keeping a dummy node and therefore this node should also be counted. Okay. So there is an initialization function that will create an empty list which consists of only the dummy node. Okay. And a pointer to that is returned. And an insert function behaves like this. It makes a sorted insertion. If the element to be inserted is already there, no new node is created. Okay. And there is a delete function. Deletes the data from the list. If the data is not present, then nothing is done. Okay. So let's say we have these standard functions, init, insert, delete. Okay. And I am not very much interested in writing those functions because these are very trivial. And init actually allocates one block of this type, size 16. And insert, if it is successful, that is, if it is an insertion of a new element, this creates another block. Okay. And appropriately links it in the linked and sorted list. Yeah. Okay. So what happens? During init, one node is created, and during every successful insert, an extra node is created. But all these nodes are currently linked by the head pointer. Okay, the head to this linked list. So they are all accessible. Only when the concept or question of memory leak comes, if you delete a data from a list. If the delete is successful, then what you are doing, you are essentially short-circuiting the some next pointer to overlook or simply bypass that node. Okay, so it's something like p next equal to p next next. Okay. And if you do so, I would say, definitely that node that you want to delete, that is deleted, but this is not yet freed. Okay. Moreover, unless you have a pointer pointing to that node, it is lost. Okay. So let us see this delete part. So as I mentioned, I always stay in the node before the deletion part. So I will start with the header, the dummy node, and I will look at the data of the next node, not that node. If that is equal to X, I will simply say P next equal to P next next and return the original list. Otherwise, I will keep on searching If p next data is already greater than x, then definitely I know I cannot find x in that list. I can immediately break. Otherwise, I will go to the next point at p equal to p next. And eventually, if the list completely ends, that is a normal exit from while. Okay. And here also you return L. Okay. So what happens here? I am making p next equal to p next next. So earlier p next was pointing to a block. Okay. I have simply bypassed that block by writing p next equal to p next next. So the earlier value of p next is never saved. Okay, that block is never, pointed to that block is never saved, and it is also not freed. Okay. Now let us do a sample run of this code. Okay. So it's insert 5, 14, 18, 4, something, some such things. So eventually your list becomes 5, 5, 14, 5, 14, 18, 4, 5, and so on. Up to this point, you are only inserting. There is no problem. No question of memory leak. Then you delete 5. So this will go 4, 8, 9, 13, 14, and so on. Maybe then you delete 5, 14, 18, 13. Eventually you delete 20. So this is this. Okay. Suppose I call insert and delete in this sequence. Okay. Then what you see, the heap summary is now not at all very, I would say, desirable. Okay. In fact, it says that in use at exit is 144 bytes in 9 blocks. So how many blocks? Init has 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 blocks. Am I correct? There is no duplicate insertion, right? No. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 plus 1 during init, so 9 blocks. Okay, each taking 16 bytes, so 9 times 16 is 144. Okay, it is still used. Okay, you have not freed anything. Okay, and total heap usage 10 allocs, 1 frees. So this is a little confusing, but in my machine, what happens is that there is some alloc and some free. This is done by the system. Okay. So although you didn't free anything, but you read it out whenever you read it. So there are some function calls, okay, which made 1 alloc and it is good. So it made 1 free. The remaining 9 allocs were done by you and you have freed none of this. Okay. So this 1 free you do not need to worry about. This is a system level thing that the machine does. Okay. And then it says that definitely lost 48 bytes in 3 blocks. 3 times 16 is 48. Indirectly lost 2 times 16, 32 bytes. Possibly lost none. Still reachable 64 bytes in 4 blocks. Okay. So let's see why. Why 48, why 32, 64, why 64, or 324. Okay. So let's see how this sequence of deletions works. So initially I have this dummy node. Then I have 4, 5, 8, 9, 13, 14, 18, 20, right? 4, 5, 8, 9, 13, 14, 18, 20. Okay. Then I delete 5. So I always stay in the previous node. When I see that it is 5, it is found. So I will simply make this pointer point to this so that this 5 is bypassed. Okay. So this is the effect of delete 5. Then if I do delete 14, I will do so while sitting here. Okay. I will simply let this pointer point to this so that 14 is bypassed. After these 2 deletes, it is 4, 8, 9, 13, 18, 20. Then what is the next delete? Okay, so this is this structure after the 2 deletes. Then I delete 18. If I delete 18, what will happen? I am sitting here. So I will let this point to 20. This pointer point to 20 so that 18 is bypassed. So I have a situation like this. 13 will directly point to 20. 18 is bypassed. Like earlier, it is still pointed to by 14. 18 is pointing to 20. Okay. Now if I do delete 13, this pointer will come here. So 13 will be like this. Okay. How many more deletes? Just one more delete. Okay. I am now deleting 20. So this pointer 9 will point to the next, which happens to be empty, the null pointer. And 20 is bypassed. Okay. So it's something 20, 80, 14, 13 is pointing to 20, 20 is pointing to null. Okay. Now you see that each of this circle is a block that was allocated by a malloc call. Okay. Now, if you exit after this delete 20 without any freeing business, okay. So you still have that header pointer to your linked list. So if you follow that linked list, you can access this, access this, access this, access this. These are not freed, but still reachable. So how many blocks are reachable? 4 blocks, accounting for a total of 16 bytes. 16 times 4, that is 64 bytes. So let's see what it said. In use that exist. Oh, sorry, it's not this one. Still reachable. This is 64 bytes in 4 blocks. So you understand what still reachable means. And this is total use. And that consists of these, and so on. Okay. So 4 blocks are still reachable when your program exits. Okay. And these 3 things, blue colored blocks, they have no pointers pointing to them. Agree or not?
Sir,
So they are, yeah, tell.
sir, what do you mean by the program exists? If the program exists, then all the allocated memory will be deallocated, right?
It should be, but Belgrade will tell you in some sample runs, maybe it's a server program, right? But you want to check whether unintentionally you have made some memory leaks. Okay, so you exit the server during development phase and you find out whether there is any such memory leak. Okay, of course, here you have written a fancy small application, but the point is that whenever we use these demonstrations, we use some, I would say, some such simple programs. But never forget that you have the basic idea in mind that you are writing big software. Okay, big pieces of code.
So we can assume this whole thing as a function in the server, and each time the function is run, this memory.
You may think about this also. You may also think about this. Okay.
Okay.
Okay. Yeah. So this is definitely lost, right? There is no reference to this.
Sir, I have a doubt. Sir, I have a doubt. There are nodes which are said to be reachable, but is it not like that the head pointer itself gets lost when the program ends, or are we assuming that it's not lost?
When the program ends, everything is lost. Okay. And if the system wishes, it will simply return this memory to your system pool. And if the system does not care about that, this will be permanently lost until your next, what is that called? Next boot, next reboot.
Okay, sir. Okay.
When we run the program again, all these nodes will be again reallocated, right?
Usually in my machine, that thing happens that when this program terminates, these things are returned to the system pool.
So let me clarify, if I may, Vijit, may I?
Yeah.
So So what you are seeing is actually what is called an address space. Okay, a program gets a set of addresses, which is backed by the actual RAM. Okay, so think of that you have some X amount of address space. When your program terminates, everything is returned. Okay, so there is no problem. But as Eddie has just told you, and one of you have also noted, that we are, you want to do this at the development phase. So before the server runs and leaks, 1 byte over 6 months, okay, you want to call the functions to see whether this function has leaks anything or not. So you will always test things in small modules, slowly building up the big system. So what it is saying is basically that if you allow it to stay, okay, then all these things are there. If the program exits, it's returned. But then if you allow it to stay, these are the ones that got lost, basically. Which means if your program does not terminate, but these things will not be reachable at all. Or these things is still reachable because there is a pointer to it, but you have not freed it. Okay, and these things I cannot really make a guess that the possibility thing basically that whether it's reachable or not. So once you terminate your program, this entire thing is gone. When you run your program again, this entire thing will be created afresh. A new malloc, new address, and so on and so forth. But you are testing things in small things to make sure that when you eventually run the big thing, okay, is there any leak on there or not? In the small programs that you run, okay, if you see you have in PDS and all, you have done malloc without freeing a lot. So these things will not matter at all. But just do this after the class, just do this. Okay, write a simple small 4-line program. It's a while one loop. Okay, and only thing you do inside the while loop is allocate one character. P equal to char star malloc size of char. But it's an infinite loop. And just run it and just wait for a few minutes and you will see what happens.
Possibly not needed to wait for a few minutes.
Just a couple of minutes. I was just running it on my old machine. Okay.
Anyway,
1 minute, yeah. So it will run out of space, get killed. Okay.
It will eventually get killed, but your system will become horribly slow and all this thing will happen.
Right.
So don't do it when you are.
While you are doing something, don't do it. Useful. But when your laptop is free or machine is free, just try. But once it is terminated, this is gone completely. The entire thing gets back to the system. Okay.
Yeah.
But
by that time, what happens usually? This memory goes to the swap area and things become extremely slow. Okay.
And the other thing that happens in the server, as I said, you will learn in third year something called threads. And threads share that same address space. So you get 10 threads, okay, they will share that one single set of addresses that were given to the process. So even if one thread that is servicing your request exits without freeing something, what it has taken out of that common address space still stays there. So no other thread for the subsequent request that comes to the server can take that space. So if you have lots of threads, each leaking like 2 bytes, 2 bytes, 2 bytes, 2 bytes, eventually the server will crash. Okay, I'm done.
Yeah. So this tool just gives you an indication what are the wrong things you have done. Yeah.
Sir, as a consequence of running that while one loop, will the system become slow like permanently or while the loop is running?
It will get killed very fast. Don't worry. It will run out of memory very fast because of a limit on the memory.
It will eventually reach segmentation fault or something like that.
It's just a killed, basically.
It will be killed.
Killed.
Okay, sir.
Okay, but don't try every now and then. It's a risky thing. Okay, anyway. Okay, so the idea is that this is just a tool that will tell you that these are the wrong things you have done. Okay, so I am just illustrating these wrong things by using this toy example. What is the difference between reachable, definitely lost, and indirectly lost? Okay, so that's the only reason I am using this example. This kind of leaks are possible in a million ways. Okay, so you can see that these blocks are called definitely lost because nothing is pointing to them. Whereas these blocks are called indirectly lost because they are pointed to by some pointers, but those pointers are coming from some other blocks which are either definitely lost or indirectly lost. Agree? So do you see the difference? Reachable, definitely lost, and indirectly lost. Possibly lost, I will explain separately later. First, let me understand that the meanings of this type of things, definitely, indirectly, and still reachable. Is that clear?
Yes.
Yeah. Yeah, any question? Okay. So, yeah. So now I will explain to you what is meant by possibly lost. Oh, no. I want to improve upon this behavior. So once you know that there is a leak problem, you figure out, you look at your code, and you definitely can free this, okay, by storing a pointer like this. Okay, it's the same delete routine, but with a free call. And you say q equal to p next, just store this pointer. Then you say p next equal to q next, that is p next, then free q. Okay, then these deletion requests will free this memory. But you still have these 4 blocks in use. So if I use this LDL, list delete, instead of the previous one, my heap summary will be like this. Now there is nothing definitely or indirectly or possibly lost, but still reachable 64 bytes. Okay. This 64 bytes, they are still reachable. So if I now use a destroy, I would say, function, which node by node frees every memory in the linked list. So while L, P equal to L next, free L, L equal to P, keep on doing this. And then if you run, okay, so you call this L destroy after this delete 20. Okay. Now if you call this, if you run Valgrind with this L destroy in place, then you will see in user exit 0 bytes, 0 blocks, okay, total heap use 10 allocs, 10 frees, so many bytes allocated, and all heap blocks are freed, no leaks are possible. So this is your ultimate goal. Agree? So whenever you see this line, you are sure that you have not made any memory leak in your program. Happy?
Yes, sir.
Good. So this is your ultimate goal. So now what remains is to show what is meant by possibly lost. Okay. So instead of doing whatever Eji suggested you to do in a loop, I have done it just twice. I allocated an array of size 10 integers to P, and instead of saying Q equal to P, Q points to the fifth one. 0, 1, 2, 3, 4, skip those, then fifth one. Okay. Q equal to P plus 5. Then once again, I allocate an array of size 5 integers to P. So this new address essentially overwrites the old address. Okay. But Q still holds a pointer to the somewhere in the middle of this array. It may be P plus 5, P plus 2, P plus 8, but not outside this. Okay. So what in effect we are doing after this when the program is going to terminate, this address is lost because that address is overwritten by this new array address. P is pointing to this. Q is not pointing to this, but somewhere in the middle. And this is called an internal pointer, an interior pointer. Okay. So the idea is Valgrind is not sure by looking at this pointer whether you have the ability to go back here and free that memory. In this case, yes. You can again say Q equal to Q minus 5, free Q. You can do that. But think of each of these cells as consisting of some records, something, some name, some CGPA, blah, blah, blah. And it contains something like a character pointer. Okay. And this pointer is pointing to that character pointer. It is no longer a node pointer, it's a character pointer pointing to a character array inside this structure. Okay. Now from that character pointer, can you identify the pointer to this entire, I would say, structure, and then come back here? I don't know. It may be, it may not be. Valgrind also doesn't know whether, despite having a pointer pointing somewhere in this allocated memory, you can go back to the beginning of that memory and free it. So that's why Valgrind is not sure. So it says it's possibly lost. Okay. So if I run this program with Valgrind, you will see it's possibly lost 40 bytes in 1 blocks. 40 bytes in 1 blocks. Why? Int size is 4, 4 times 10, 40, and this is only 1 block, 40 bytes. And still in use, this P, 5 times 4, 20. Okay. So possibly lost 40 bytes in 1 block, still reachable 20 bytes in 1 block. Okay, so do you understand? Yeah, tell.
Sir, block means a continuous section of memory, right?
Block means whatever you have allocated.
Like array is of size 10, but it is showing just 1 block. So is it means, but however in linked list it was showing one block for each node.
Look, I have somewhere written it. Let's see. Okay, each malloc or calloc or realloc call allocates a block. That may be a single node, that may be an array of 10 nodes, that may be an int array of size 100. Each such allocation gives you a block. Its internal data structure you don't need to worry about. I mean, this Valgrind doesn't need to worry about. Okay.
Okay, sir. Understood.
Okay. So it's 4 blocks, 64 bytes. But in this case, 1 block is same as 1 node. In this case, this malloc call gives a block whose size is 10 times 4, 40. This malloc call gives you a block of size 5 times 4, 20. Okay. So it's not an individual cell.
Okay, sir.
Okay. So what should you do? You should free. Okay. So that's one thing, memory check thing. Now comes the second part. So it may be a standard error. So I am allocating an array A of size 16. Okay, it's anyway dynamic memory. Okay, anyway. So A starts at this and ends at this, that is fine. Then I want to compute I square from A1 through AN, from for I equal to 1 through N. And I have allocated a memory of size 16, but I am accessing, storing in AI, I star I for I equal to 1 to N. Okay. I don't think this kind of errors are very likely. Okay, but also you see that this is one block and you free it. So there is no memory leak here. Okay, you allocated this memory. You got one block of size n star whatever 4n bytes. You free it. So it is free from memory leak. But you are supposed to access only the array indices 0 through n minus 1, and here you are doing it 1 through n. Okay. So now if you run this program with Valgrind, when it is running, it will issue some warning messages like this. Invalid write of size 4. Invalid read of size 4. What is invalid write? This is invalid write. Because you are writing I star I in AN. That is invalid. This is beyond the array location. And this is invalid read. You are reading AN, which is outside the array, printing it. So this is invalid write, this is invalid read. Okay. But with respect to leak, this is good. All heap blocks are freed, no leaks are possible. And you see that this error comes not at the end. Before you print, these things are written. So in runtime, it can detect these errors. Is that clear? But if you simply run a.out, you will never see these messages. Yes or no?
So the code will compile or will we get segmentation fault?
It depends. It will compile anyway, because compile time there is no check, range check. It will compile. If you run it, most likely it will run and it will give you this. Okay. Only thing that it will do this bad thing silently, most likely. And if you encounter segmentation fault, then of course you know that there is something wrong. But the idea is this: even if you notice nothing wrong in a normal run, there may be something wrong. You run this without Valgrind, most likely it will run like this and it will freely terminate. Okay, it will normally terminate without any problem. This is the expected behavior. Okay. And so by running ./a.out alone, you do not know that there is something wrong. If you encounter segmentation fault, definitely you know that there is something wrong. Okay. But if you do not encounter it, you do not know that silently you have done something very bad. But Valgrind will identify your mistake here. So two errors from two contexts. One is invalid write, one is invalid read.
Okay, sir.
Okay.
Yes, yes.
Can I add a line?
Yeah, you please.
So this is what is called the buffer overflow or heap corruption, goes in different names in different OSs. And this is, if you get a segmentation fault or access violation, depending on the OS, it's very good news. Trust me. Then you know something is wrong. Otherwise, this is one of the toughest errors to debug. Because it will silently overwrite something, then that value is used by some other value, which is used by some other value. So the error will actually come out as something very strange. And then you have to debug all the way back as to why is this happening, which value is wrong in a function call. It should have been 13, but it has become 17. Okay? So this is one of the toughest errors to debug if the segmentation fault does not happen. So again, like when you develop code, it's very good to have this kind of tools to actually find these things out. It's very, you have seen this error a lot in PDS. You did I equal to 0, I less than and I plus plus. Instead of less than, you have done a less than equal to. So just added one more thing. Now, if nothing important is there, you are fine. but then that to the system is free. The system would have allocated that to something else. So you're just silently overwriting its value sometimes, or reading a wrong value from there. So be very, very careful about this error. Okay, I'm done.
Yeah. Yeah, so this is also an example of buffer overflow, but technically buffer overflow usually refers to character arrays. So what here I am doing, I am using a dynamic character array size 32, and the user runs with something like some on command line argument, which I convert to actually not convert, I yeah, I am just saying welcome to, and this whatever argv1. So this is called sprintf. This is like printf, but instead of printing to your terminal, it will print to this string w0. And you say %s print this w0. Okay. So one thing possibly. Okay, no, it's not there. Oh, yes. You can see. You can identify where you have this problem. See that A starts at this, ends at this. These two addresses you get, but this invalid address is 0x4A5A080. So it's beyond 7C. Okay, so it also helps you identify which address is corrupted. This is also important. Okay, this address 080. Yeah, 07C. Ends not exactly at this, plus 3 bytes, CDE. CDEF. Yeah, 80 is the address outside your array. Okay, int is 4 bytes. Okay, this also identifies where exactly it's happening. So if you then watch this, I would say, starting and ending address, so you also get it. So it starts at this, ends at this. And then compile and run as follows. Again, I said there may be no errors. If there is an error, you are lucky. Okay, you know that your program has something wrong. But if it silently observes, or if it silently, I would say, runs this, okay, you do not understand there is anything wrong. What is the size of this? 1, 2, 3, 4, 5, 6, 7, 8. Maybe 31 or something. Okay. 31, and you are adding 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 plus 31. That is 42, plus you need that trailing null character because this is a string. Total 43 bytes, whereas you have allocated just 32 characters to this dynamic array. Okay, but you are storing some 43-bit string, not 43-bit string, I would say a 43 character string, including the trailing null character. Okay, but still, with high probability, you will be unlucky and see no error when you simply say /a.out systems programming laboratory. Okay, but in order to see that there is something wrong, once again you run using Valgrind, and then you see starts at this, end at 5F, and you see you have some invalid access 6069, 6068, 66. Okay. As far as my experience goes, every time, I mean, it's character by character, but possibly it does not say 60, 61, 62, 60, 64, but some of these messages are given. Okay. But it's possibly counted everything, 38 errors from 6 contexts. So once again, this is invalid read and invalid write. Oh no, yeah, invalid write. Why is it invalid read? Oh, yes, yes. This is invalid read. This is invalid write. Okay, you're assigning things there in W naught and you are reading things from W naught. Okay. So, yeah. So that's it.
Sir?
Yeah.
Sir,
So we created a buffer memory to W naught, right? Then I did not get what is that argv1 and all.
ArgC you didn't study? In the very first set of slides, we told you to. There is an appendix part. Okay. So you run your thing something like this, error out something, or you say ls minus l minus p tilde. So how does the program knows that you have said minus l minus p and tilde? So it is stored in this array. And how many, what is that called, arguments are there? This is stored in an integer variable. Okay. So you read that thing. Okay. But anyway, this kind of string related problems are possible for strcpy and many other things. Okay, wherever you write a string and go beyond the allocated location. Okay. sprintf is one of this. strcpy is possibly a culprit and all that stuff. Okay. Even your getS function may corrupt memory, and buffer overflow is actually a source of some possible attacks against some crypto systems. Not exactly crypto systems, but your your system. Okay. So the earlier thing also can be called a buffer overflow, but buffer typically refers to character.
sir,
Okay, tell.
sir, in this in the output, sir. Sir, here 0 bytes and then after 9 bytes and then after 0, 8, 6 bytes. Sir, means I'm not able to get this thing, sir.
0 bytes after. Okay, I will explain. How do I explain? I do not have. Okay, so let's see. This starts at 40, ends at 5F. So what is the byte after this? In hex?
60.
60. So after this allocated size, this is the 0th byte. And 9 bytes after this allocation portion is 69. 68, 8 bytes, 66, 6 bytes. And earlier also you will see this ends at 7 CDEF. After that you have 80. So 80 is the first byte. Okay. But it's 0 bytes after a block of size 64 alloced. Is it clear now?
Yes, sir, but after 9, 8 is coming and then after 6 is coming. So why is that?
Oh, so you mentioned this 09 is this thing.
Yes, sir. Yeah. 0, 9, 8 and 6.
Actually, you should see everything 60, 60, 61, 62, 63, 64, yes, but sir. It does not do this. Okay. And that reason is not extreme. I mean, not very clear to me why. Okay, but anyway, you will get some error messages.
Okay, sir.
Okay, and that's sufficient for you to be careful. There is something wrong with your code. And possibly you, what would I say, would no longer argue with your TA that no, sir, this is working fine in my machine. Your machine has a bug. It's most likely no. Your program has a bug. Okay, I think that's all we wanted to talk about for Valgrind. Yeah, tell me if you have any immediate question. No?
Hello. What happened?
What happened? Yes.
No, they're there, I think.
They're there, but it's complete silence. Why?
अरे कोई तो कुछ बोलो यार. Can you hear us?
Yes, sir. Yes.
Yes, yes.
Yes, sir. We can hear.
Okay, so they're ready. Go ahead.
Sir, how is Valgrind able to get the information of lost memory if they are lost?
Not important to you.
Not important to you, but anyway, the system has to keep track of it. Otherwise, it cannot free. When a program terminates, it cannot do the extra bookkeeping work for you, which you didn't do.
Valgrind injects code. Valgrind injects code in your editor. But how, why, etc., you will not understand now. Which is why when you run it through Valgrind, it will take longer time. But that's okay because you are doing it only during development to debug things.
Sir.
Yeah.
Sir, when I run the command sudo snap install valgrind, the terminal shows that this may perform arbitrary system changes and may put my system at risk. Like that sort of error is showing in the terminal.
What Linux are you running?
Ubuntu 20.04.
I also use the same thing.
Means there are two options: sudo snap install and sudo apt install. So
go for sudo apt install. I don't think you will get that. It's just a general warning it is giving because it doesn't know what you are trying to.
Yeah, I also prefer apt, but sometimes I have to use snap. Oh, you tried snap?
Yes, yes.
Okay.
I will try it with apt as well.
Yeah. I think that that is fine.
Yeah, that error is it doesn't know what Valgrind is, so it's generally telling you that you're trying to install something, it may make changes and so on. This is like when you try to install a new software in Windows, remember it asks you something is going to make change, are you allowing it or not, and so on.
It executed with apt.
Okay, so anyway, it's an important tool you should be acquainted with. And next time when before you ask your TAs about, oh, it is running in my machine, it's not running in your machine, so your machine has a problem. So before telling or making some such claims, you first run Valgrind. Most likely you will identify that your program has some error. Okay. Yeah. So no other questions. So how many? 120 approximately.
Sir,
yeah.
Sir, I have a question, right? Let's say I'm making something where I ask the user to put some input and as a string, and like if someone wants to break the system, they can obviously just put a big input, right, and cause buffer overflow.
Yes, this is one of the source of a problem. This is called buffer overflow problem, and it's because of this. This gateS is no longer, I would say, appreciated. Okay, so if you write the getS function, try to compile, then the machine will say, do not use getS, use fgetS. Okay, but anyway, if you are not careful, this kind of memory leaks and attacks are still possible.
Okay.
But you see, this is something. This is not an inadvertent thing. So suppose you have a 100 size buffer, okay, and you ask for a scanf a string, and then somebody gives you a very large string, basically more than 100 characters. So there are two possibilities. Okay, either basically that after 100, because there is a protected memory and all, you will get a segmentation fault, in which case something is wrong, or it may overwrite. Okay. But see, in this case at least, you can figure out, you can put a very easy check actually to see that how many characters have we actually read till the \0. So you can figure out basically easily by putting a 2-line check that whether this something has been overwritten or not, whether you have inputted something more than what your buffer size is. Whereas the other errors that he is talking about is more about not knowing, inadvertently doing this basically. So yeah, go ahead, please.
So whenever we input strings and all, if we're not sure what is going to happen, we should always put a check. If something is going wrong, we should just discard that.
Theoretically, right? Yes. Or as Eddie has said, okay, you can use fgetS and other things which allows you to say what is the maximum that you are going to read, basically. So your system will not read more than that. fgetS has a parameter for that, right, Eddie?
Yes, yes.
So rather than, yeah, what is the maximum number of characters that you are allowed to read from the keyboard? You can specify that as a parameter to the call.
Okay, sir, understood.
Rudrak, your original question is answered. You understood that?
Yes, sir.
Okay.
Yeah, anything else?
So along with this, look up the GCC warnings. Okay, so GCC has a warning about unused variables, uninitialized variables, and so on. Okay, so take a look at that also again, basically. So if you are using an uninitialized variable and for the first time without initializing and all, it's a very common cause of that. It's running on my machine, not running on your machine kind of deal. Okay, I think GCC gives you a warning on that, has a option to get a warning on that also. So, Eddie, should we tell them about the exams? We have to send the mail anyway.
Okay.
So, 15th February, in class, you will have a short test. Okay. So, we'll decide how short is short. So, it will be a Moodle based test in which you will have to answer many things. So, shall we keep I think we'll keep the syllabus till Valgrind, Eddie? Till today?
Fine.
Yeah, I think
next week's stuff, but anyway, it doesn't matter.
Yeah, so let's see. Next week we do GProf, right?
Yeah.
Yeah. So let's see. Let's keep GProf out. Let's go up to Valgrind.
Okay.
So we'll test how much you have practiced yourself a little bit. It'll be simple things, but still.
But it's not a programming.
Right. So you don't have to write C code or something like that. But we make just a sample thing, like we may give you some dependencies, ask you to write a small makefile. We may ask you, if you give you a small program and say, if you do GCC on this with this warning, what will happen? Mostly things that we have asked you to study from the materials that we have given, not the entire GCC manual or anything. So we'll send out a mail again, but there's an advance notice. Okay, so any other questions, anything?
Okay, so yeah, if there are no questions, let us stop this session.
Yep, I think so.
Yeah. Okay, see you.